Hello, my name is Chanyoung Park from UNIST. I will briefly introduce our work on selective on-device execution of data-dependent lead IOs. Modern storage devices have significantly advanced in speed and bandwidth. The evolution introduces two issues that were not present. The first issue is that there is a bandwidth gap between PCIe and storage internals. This graph shows a significant increase in internal storage bandwidth, but while the PCIe interconnect bandwidth has been unchanged. So the data movement becomes a bottleneck even with high internal storage bandwidth. To solve this issue, in-storage computing offloads data-intensive computations into the storage device to reduce the data transfer between through the PCIe. In-storage computing leverages the high internal storage bandwidth for throughput-centric workloads such as grab and KNN. And in-storage computing implements computational storage devices by integrating high parallel on-device processors such as FPGA. One of the in-storage computing examples is Insider, which proposes FPGA-based programmable computation offloading. As another example is called Lambda.io. It also offloads data-intensive computations into the storage, similar to Insider, but enhance its efficiency by enabling fast data access, particularly in areas like page caches. And the second issue from the evolution of modern storage devices is that the kernel software stack emerges as a bottleneck as storage devices become faster. When we check the kernel software stack latency on an NVMe storage device, nearly 48% of the latency came from the kernel software stack. To tackle this issue, in-host near storage computing reduces the kernel software stack by offloading latency-critical computations closer to the storage device. For instance, XRP enhances the performance of data-dependent read IOs, which refer to read-only large on-disk data structures commonly used by storage engines. XRP repeats the executing an eBPF function within the kernel and submitting necessary read operations to bypass the kernel software stack. We call these operations that requires consecutive read requests as a resumption task. Impressively, we observed that existing in-storage computing primarily focus on throughput-centric workloads, not latency-critical cases. So our research explored the topic of whether in-storage computing can expedite data-dependent lead IOs as an example of latency-critical cases. However, we found that the characteristics of in-storage computing do not fit in latency-critical cases. The first characteristic is that computational storage devices have low computing power. Common approaches optimize throughput-centric workloads by using high parallel on-device processor. However, this kind of processor can increase the on-device computing latency since the low computing power reduces the advantage of lower data access latency. The second characteristic of in-storage computing is that commercial computational storage devices are not designed for the potential advantage of access latency. For example, in the Samsung Smart SSD, the FPGA and the SSD controller are connected via PCIe. Eventually, their access latency is not significantly lower than that from the host processor because of the communication cost between the controller and the on-device processor. These two characteristics creates two constraints, making it difficult to consider latency-critical workflows. First, we must consider the limited computing power because moving heavy tasks to on-device may negatively impact overall performance. Second, the on-device processor must be located possibly closer to the controller. In other words, the device should not have a considerable communication cost between the controller and the on-device processor. In this time, considering this constraint, we propose selective on-device execution of data-dependent lead IOs called SOD. SOD shows how on-device computing can be effective in data-dependent lead IOs where a read-receive data transfer is not beneficial. And SOD introduced hybrid resubmission that selectively balances on-device and in-storage in-kernel executions to consider the limited computing power. Moreover, SOD assumes that the on-device processor is located possibly within the same system on chip as the storage controller to eliminate the communication cost between the controller and the on-device processor. Let me show how hybrid resubmission works. When an application submits a request to the storage, SOD prepares metadata to handle on-device and in-kernel resubmission tasks. And SOD sends the metadata by extending an NVMe command, and the storage device performs a read operation. Once the read request is completed, on-device runtime can perform an on-device resubmission within the storage. If the further resubmission is needed, the runtime completes the request. However, the on-device processor can have no resources because of the low computing power. In this case, performing in-kernel computing can be more effective in terms of latency rather than waiting for a task to complete. We call this offloading process reverse offloading. The offloaded tasks can execute faster on the host CPU, which has better computing power than the on-device processor. However, these offloaded tasks experience about 500 nanoseconds to 1 microsecond of PCI round-trip penalty. Interestingly, we observed that the hybrid resubmission can have latency critical cases despite the penalty of reverse offloading. This is an example of how SOD operates during B+3 index lookups. SOD can traverse read-only large on-disk data structures similar to XRP, and SOD patches node and parse them and repeat these data-dependent read requests. If the on-device processor has no resources, reverse offloading can complement the low computing power of the on-device processor. Our paper presents more design choices we made for SOD as shown here. In this case, SOD caches PIR metadata to translate PIR offset for on-device and in-kernel resubmissions. And SOD supports parallel execution for heavy on-device resubmission tasks, and also emulates sandboxing overhead with MPK. Today, I will skip this part due to the limited time. To implement the SOD prototype, we extend NVMeVirt, a realistic software-defined emulator for NVMe storage devices. We select Intel Optane DC SSD model to use ultra-low latency storage devices, and we choose the ARM Cortex-A53 as a reference for our on-device processor because the ARM CPU has been used as a storage controller in the prior work. And importantly, we limit CPU performance to emulate a WinP on-device processor based on the results from our micro benchmarks, which mimics key value store lookup operations. In the experiment, we found that lowering the CPU frequency to 1.20 gigahertz is a reasonable way to emulate a WinP on-device processor, since the result of the ARM CPU has a similar performance as the Intel CPU with limited frequency. We evaluate SOD in this environment. Especially, we use 192 gigabytes of memory and a single NUMA node for computational storage emulation. And we bind four cores similar to our reference processor, ARM Cortex-A53. We assign one resubmission worker to each one, and we use a simple B+ tree key-value store called BPF-KV for our evaluations. And we also test SOD on WiredTiger for real-world evaluations. The first takeaway from the evaluation is that SOD effectively eliminate kernel support stack overhead and PCIe round trip. When we evaluate SOD and XRP in BPF-KV with varying thread in the closed loop load generator, SOD achieves higher throughput and lower latency than XRP. Notably, on-device handles 38% of requests, while in-kernel handles the remaining 62%. The second takeaway is that SOD performs better than the on-device execution alone and the in-kernel execution alone. When we evaluate SOD on BPF-KV with an open-loop load generator suitable for stress testing, SOD's hybrid resubmission delivers higher performance than on-device execution alone, and using on-device execution alone cannot achieve better performance than XRP, which is similar to our in-kernel execution alone. This result highlights the disadvantages of on-device computing for latency-critical workloads due to its characteristics. And SOD has 10.8% better performance than XRP. We can understand that this hybrid approach can help latency-critical cases. We also evaluate SOD on WiredTiger, a widely used log structure merge tree-based key-value store. We test WiredTiger with YCSB workloads. The result shows that SOD reduces resubmitting system call latency by up to 9.4% compared to XRP. However, SOD does not reduce the latency when running workload D, because the on-disk tree depth is swallow, resulting in a small number of resubmissions. It means that SOD cannot achieve more optimistic resubmission inside the on-device side because of the small number of resubmissions. Here is the conclusion of this talk. We observed that the characteristics of in-storage computing do not fit in latency-critical cases. SOD is designed under some assumptions due to these characteristics. Thus, SOD provides a new design with hybrid resubmissions, which selectively utilizes on-device and in-kernel computing. In the evaluations, SOD achieves better performance than approaches that are entirely relying on either on-device or in-kernel computing. Thank you for listening to my presentations.